The surface of a still lake seems perfectly smooth until a breeze runs across it. Ripples expand in graceful circles, merging and fading into one another with no visible seams. From a distance, it appears as a single continuous motion, like silk folding and unfolding. But lean close enough, and that illusion begins to shatter. Each ripple is built from countless molecules of water, each jostling and colliding according to the laws of atomic motion. The seeming continuity hides a restless discreteness beneath it. The same might be true of everything we call space and time. Imagine a photograph on a bright screen. From far away, it is a perfect image, rich with detail. Move closer, and the picture dissolves into a grid of pixels, square bits of light that together mimic smoothness. Our senses are tuned to see the whole, not the structure beneath it. The cosmos, too, might be a projection of something deeper, a resolution so fine that our instruments and eyes cannot yet distinguish its individual dots. When Einstein described space-time as a smooth fabric, he gave us a map that bends and stretches seamlessly. Yet that smoothness might be as deceptive as the calm surface of a lake or the glow of a digital image. In classical physics, the universe is continuous. Space can be divided without limit, and between any two moments of time lies another and another, without end. Equations of motion depend on this assumption. A falling apple, a spinning planet, a photon traveling through a vacuum, all follow curves that can be sliced infinitely fine. Every point leads to another point, and the geometry remains unbroken. The very tools of calculus, the foundation of modern physics, require this unending divisibility. Without it, the derivatives and integrals that describe motion, energy, and curvature would simply fall apart. Einstein's general theory of relativity perfected this vision. It transformed gravity from a force to a property of geometry. Matter tells space-time how to curve, and curved space-time tells matter how to move. The mathematics of that curvature relies on tensors, continuous fields defined at every point. These fields can vary smoothly, describing how a planet dips the surrounding space, how light bends near the sun, how the universe itself expands. Nowhere in the equations is there a smallest step, a pixel, or a gap. One could, in principle, zoom in forever, and space-time would remain the same kind of fabric, ever smooth, ever divisible. Yet reality has a habit of defying infinity. Nature sets limits. No ruler can measure with infinite precision. No clock can tick infinitely fast. When we descend into the quantum world, the comforting smoothness of classical geometry begins to tremble. The smaller the region we try to observe, the more energy we must use to probe it, and at some point, the energy itself distorts the very space we are trying to measure. A photon of high enough energy can warp space-time through its gravity, creating a tiny black hole that hides the region from view. There, the notion of a continuous geometry breaks down completely. Theoretical physicists have given this boundary a name: the Planck scale. It marks the smallest length and time that makes sense in our current understanding of physics. The Planck length is about 1.6 times 10 to the power of minus 35 meters, and the Planck time is about 5.4 times 10 to the power of minus 44 seconds. Below these scales, quantum uncertainty and gravitational curvature merge into something unknown. The fabric of space-time may no longer behave like a fabric at all. It might fluctuate violently, like boiling water seen under a microscope, where smooth surfaces erupt into froth and chaos. To visualize this, imagine zooming in on an ordinary piece of cloth. At first you see texture, then threads, then fibers, and finally atoms. If space itself has a similar substructure, the continuous curves of Einstein's equations might be only an approximation, the large-scale view of an underlying lattice. Each unit of space-time could be a quantum of geometry woven from something not yet understood, perhaps loops, strings, or informational bits. From far away, these elements blend into a seamless continuum. Up close, they might reveal a discrete architecture as intricate as the weave of a fabric. What if the apparent continuity of reality is an illusion born of scale? A river looks unbroken even though it is made of individual molecules. A beam of light seems smooth, yet it consists of photons. Perhaps space and time too are emergent averages, not fundamental entities, but collective phenomena arising from something deeper. In that case, the equations of general relativity would be like fluid dynamics, powerful and accurate for describing the flow, but blind to the molecular chaos beneath. The question of discreteness strikes at the heart of physics. It is not merely about measurement or technology, but about the nature of existence. Is the universe ultimately countable? Could every second, every meter, every unit of reality be built from indivisible quanta as matter and energy are? If so, then continuity itself would be a convenient fiction, a language for describing a world too vast to resolve one grain at a time. The challenge is to find where that fiction ends. To test such an idea, we must approach the Planck scale, the realm where gravity and quantum mechanics collide. It is there that the limits of divisibility reveal themselves, where the smooth curves of spacetime may dissolve into the granular structure of something more fundamental. The journey to that frontier begins with understanding how small is truly small, and why the universe seems determined to keep its smallest secrets hidden. The Planck length is unimaginably tiny. To grasp it, consider that a single proton measures about 1 trillion times larger. Even if we magnified a proton until it filled the solar system, the Planck length would still be smaller than a grain of sand within that cosmic sphere. It is the scale at which our mathematics begins to break apart, where the very definitions of distance and duration lose meaning. Beyond this, spacetime can no longer be treated as continuous. The smooth coordinates that describe stars and galaxies dissolve into a fog of uncertainty. Yet this boundary is not drawn by choice, but by the laws of nature themselves. Quantum theory tells us that everything exists in a haze of probability. A particle's position cannot be pinned down exactly. Measuring it more precisely in one way blurs it in another. Combine this uncertainty with Einstein's insight that energy curves spacetime, and a paradox emerges. The more energy we use to locate a point in space, the more we warp that space through gravity. Push the precision far enough, and the measuring energy itself collapses the region into a miniature black hole. That means there is a fundamental limit to how finely we can divide reality. Nature enforces a smallest possible scale, a quantum grain to existence itself. At this depth, even the concepts of before and after begin to lose coherence. Time, too, becomes subject to the same quantum haze. Imagine a clock so small it ticks once every Planck time, about 5.4 times 10 to the power of minus 44 seconds. That tick would be meaningless, for the uncertainty in the clock's own energy would blur its moment of action. Time, as we understand it, dissolves into a foam of possibilities. In that frothing sea, our classical intuition is powerless. The equations that describe planetary orbits or electromagnetic waves offer no guidance. Instead, we enter a regime where gravity and quantum effects intertwine inextricably, demanding a new language of physics. Theorists often call this turbulent realm spacetime foam. At scales near the Planck length, spacetime may no longer be a smooth arena, but a bubbling field of constant fluctuation. Tiny wormholes may appear and vanish. Virtual particles may drag spacetime into brief distortions, like bubbles rising and popping on the surface of boiling water. Every region of the universe would shimmer with impermanence. What we perceive as emptiness would be anything but empty, a storm of geometry too fast and too small for even the most sensitive detectors to capture. To picture it, think of the ocean. From a plane, it looks flat and blue. From the deck of a ship, it rolls in waves. Dip your face into it, and you see a chaos of droplets, eddies, and foam. Spacetime, too, might appear perfectly smooth from afar, on the scale of galaxies and clusters, but beneath that surface, it could churn with microscopic structure. Each fluctuation would be a twist in the geometry of existence itself. This idea challenges our deepest notions of what it means for space to exist, and it invites a new question. Is the foam the foundation, or is it yet another mirage hiding something even more fundamental still? The Planck scale acts as a cosmic censorship law, preventing us from probing deeper. Our most powerful accelerators can reach energies 1 trillion times smaller than required to resolve this limit. No experiment can currently see that fine, no instrument can record such rapid fluctuations. Even so, the mathematical structure of quantum theory and general relativity together implies that this limit is real. We cannot step beyond it with the tools of classical reasoning. Every attempt to do so leads to infinities, singularities, or contradictions. When physicists speak of unifying quantum mechanics with gravity, what they truly seek is a way to describe what happens at or below this boundary. The smooth spacetime of Einstein's equations might thus be like the calm surface of a sea, useful for describing large waves, but blind to the restless foam below. Our entire macroscopic universe, from the orbit of the moon to the curve of a rainbow, unfolds safely above that line, where smoothness holds. But beneath, the equations break apart. It is not merely a failure of technology, but a limit built into nature's code. To understand what lies beyond, we must rethink what we mean by space, by time, and even by reality itself. Perhaps discreteness is not an imperfection, but a fundamental truth, a kind of digital foundation beneath the analog illusion of the cosmos. Yet we must be careful. Discreteness does not necessarily mean that space is a grid of tiny cubes, or that time ticks like a cosmic clock. It may instead mean that the quantities we measure, area, volume, duration, take on only certain allowed values, like the energy levels of an atom. Between those levels, no physical state exists. The universe might leap from one configuration to another, so rapidly and finely that the transitions blur into apparent continuity. If so, continuity would be a grand illusion born from immense complexity. The equations of relativity would then emerge as statistical averages, not fundamental laws, but effective ones. Like the smooth surface of water made from countless molecules, the smooth curvature of spacetime might arise from deeper quantum structures. What we call geometry could be a collective pattern of microscopic interactions, governed by principles still hidden from us. This is where our journey turns from the familiar to the mysterious. If the continuum fails at the smallest scales, we must search for a theory that replaces it, one that unites the granularity of quantum mechanics with the geometry of general relativity. Such a theory would not simply describe matter within spacetime. It would describe spacetime itself as a quantum object. To find it, we must first understand how gravity behaves when it is treated not as a curve, but as a quantized entity. That search leads us toward the frontier of quantum gravity, where the building blocks of spacetime may finally reveal their shape. At the edge of our mathematical understanding, physics begins to turn philosophical. We are forced to ask what it means for something to exist when the concepts of distance and duration no longer apply. The equations of Einstein describe a fabric that can bend, stretch, and ripple, but those motions assume the fabric itself is continuous. Quantum mechanics, however, tells us that nothing can be measured infinitely precisely. If every attempt to define a point in space or an instant in time collapses into uncertainty, then perhaps points and instants are not real at all. Perhaps they are illusions born of our attempt to impose continuity on a world that has none. To imagine this, Picture a movie playing on an old reel projector. Each frame is a still image, but when shown in rapid sequence, our eyes interpret motion. The story seems to flow continuously, even though it is built from discrete moments. What if time itself is like that? Each Planck moment could be a single frame in the cosmic film, each separated by the tiniest possible interval. Between those frames, there is no flow, only the jump from one configuration of the universe to the next. The sensation of continuity would then be a trick of perspective, the way our brains smooth out rapid changes into a seamless experience. This analogy, though imperfect, helps us grasp a strange possibility. The flow of time may not be fundamental. It might emerge from a deeper process in which the universe continually updates its state according to quantum rules. Like a vast computation running at an unfathomable speed, reality might advance step by step, not in a smooth glide, but in a sequence of discrete transitions. Each step would be so tiny that even the most sensitive clock could never detect the gap. To us, it would feel like an unbroken stream, yet beneath it, the universe might tick with a rhythm beyond comprehension. Such ideas are not mere imagination. They arise naturally from attempts to merge quantum theory and relativity. When one treats spacetime as a dynamic entity subject to quantum fluctuations, it becomes clear that smooth geometry cannot survive at all scales. The mathematics predicts fluctuations in curvature, topology, and connectivity. In this chaotic regime, even the dimensionality of space might change from moment to moment. Some theories suggest that at the Planck scale, the universe behaves not as four-dimensional but as two-dimensional, flattening into a quantum network that only appears three-dimensional when averaged over vast distances. In such a view, the familiar expanse of space would be a large-scale illusion. The implications reach far beyond physics. If the universe is discrete, then infinity itself loses its power. There can be no infinitely small or infinitely large, no endless continuum stretching beyond comprehension. Everything would be countable in principle, though the count might be unimaginably vast. The cosmos would become a finite system of information, a grand digital architecture, rather than an infinite analog wave. Philosophically, this redefines our place within it. We would no longer inhabit a boundless, smooth expanse, but a quantized structure, a cosmic mosaic in which every piece, no matter how small, is essential. Yet there is another side to the story. Continuity works. It has guided every triumph of physics for centuries. From the orbits of planets to the curvature of galaxies, the smooth equations of relativity predict with unmatched precision. No experiment has ever revealed a flaw in that smoothness. The challenge, then, is not to discard the continuum, but to understand why it works so perfectly at our scale. If discreteness lies beneath, it must reproduce the continuum so well that even our most sensitive instruments cannot distinguish the difference. That hidden perfection is the hallmark of an emergent phenomenon, where microscopic chaos gives rise to macroscopic order. We stand then at a crossroads between two visions of reality. In one, spacetime is a continuous field, stretching infinitely in all directions, divisible without end. In the other, it is a granular structure, woven from discrete quanta of geometry. Each vision is powerful, each incomplete. The continuum explains the grand sweep of the cosmos. Discreteness promises to explain its deepest secrets. The truth may not lie in choosing one over the other, but in discovering how they coexist, how smoothness emerges from grain, how flow arises from steps, how the infinite is born from the finite. For now, we must accept that the illusion of continuity remains unbroken. Every observation, every experiment, confirms that space-time behaves as though it were smooth. But the mathematics whispers otherwise, hinting that beneath the calm surface of the universe lies a roiling sea of quantum geometry. To reach that sea, we must follow the trail of the smallest possible scales, where measurement, motion, and meaning itself begin to dissolve. There, in the domain of the Planck length and the Planck time, we may find not the end of physics, but its rebirth, a new vision in which the discrete and the continuous are but two faces of the same cosmic truth. The journey into that frontier begins with a single question: how far can we divide reality before it ceases to make sense? To find the answer, we must confront the limits of divisibility itself, the boundary where measurement fails and the very notion of continuity collapses. And so we turn to the edge of the known, to the realm where space-time begins to unravel, and new physics must take its place. That is where the next chapter begins. To speak of limits is to speak of boundaries, the places where old laws surrender and new ones begin. The Planck scale stands as one of those boundaries, an invisible horizon beyond which our theories lose their meaning. The numbers describing it are astonishingly small. The Planck length is about 1.6 times 10 to the power of minus 35 meters, and the Planck time is about 5.4 times 10 to the power of minus 44 seconds. These are not just measurements of smallness, they are the smallest units that can exist in the language of modern physics. If we could somehow shrink ourselves to that realm, every familiar notion, distance, duration, even cause and effect, would dissolve into abstraction. At human scales, and even at atomic scales, we move in a world that feels infinitely divisible. You can cut a line in half, and then in half again forever, at least in thought. The logic of calculus and the structure of geometry depend on that assumption. But the Planck scale whispers that this intuition is false. Beyond that length, to speak of half loses meaning, because the very concept of division presupposes continuity. Just as there is no smaller note than the quantum of light known as a photon, there may be no smaller step than the quantum of space itself. This revelation arises not from speculation, but from the meeting of two titans of modern science, relativity and quantum mechanics. Einstein's equations tell us that mass and energy curve spacetime, while quantum theory tells us that energy comes in discrete packets. When you combine the two, you find that concentrating enough energy into a small region produces a gravitational distortion so intense that it forms a miniature black hole. The act of measurement itself collapses what you're trying to measure. This is the ultimate limit of divisibility. You cannot probe a distance smaller than the Planck length without destroying the very space you wish to observe. Imagine trying to measure a point on a sheet of rubber using an extremely sharp needle. The sharper the needle, the more it stretches and tears the sheet. At some scale, the act of pointing itself becomes impossible. So it is with spacetime. To identify a position with ever-increasing precision, we must use photons of ever higher energy, but at the Planck energy, about 1.2 times 10 to the power of 19 giga-electron volts, the photon's own gravity would curl spacetime into a singularity. Measurement fails, and geometry becomes self-defeating. This boundary is more than mathematical. It represents a fundamental limit to knowledge. Below the Planck scale, the distinction between space and time, between inside and outside, may lose meaning altogether. The structure of spacetime becomes probabilistic, fluctuating violently in a phenomenon known as quantum foam. In that foam, distances stretch and shrink unpredictably, tiny black holes flicker in and out of existence, and what we call nothingness becomes a storm of energy. Visualize it as a seething ocean. From above, it looks still, but dip your finger into it and you find turbulence, eddies, and swirls beyond imagination. Every cubic Planck length of space could contain an entire universe of fluctuations, appearing and disappearing faster than any clock could ever record. The deeper one looks, the less there is to hold on to. It is as if the universe resists being seen too closely, as if nature has drawn a curtain to conceal her smallest theater. Physicists describe this interplay of uncertainty with remarkable precision. The Heisenberg principle tells us that the more we know about a particle's position, the less we can know about its momentum. The same rule applies to spacetime itself. Try to fix a point too sharply, and energy uncertainty grows until spacetime collapses into chaos. In this way, quantum mechanics and gravity form a kind of self-protecting symmetry. The universe preserves its smoothness at large scales by refusing to allow infinite sharpness at small ones. Some have suggested that these limits might hint at a digital foundation to reality. If there is a minimum length, perhaps space is composed of finite units like pixels on a screen. But there is an important difference. Pixels are rigid, Planck units are not. They represent not static bricks of space, but the smallest meaningful measurements of geometry. Between them lies not emptiness, but uncertainty, a blur of possibilities, not a lattice of cubes. The discreteness here is subtle, more like the granularity of probability than the regularity of a crystal. For centuries, philosophers and mathematicians imagined that division could proceed forever. Zeno of Elea, in his Paradoxes, questioned whether motion itself was possible if every journey required crossing an infinite number of halfway points. Calculus eventually resolved the paradox by accepting infinity as an idealized limit. But physics, grounded in measurement, cannot indulge infinity so easily. It must deal with what can, in principle, be observed. And observation ends at the Planck scale. There, Zeno's infinite divisions find their natural stop. What does this mean for the continuity of the cosmos? It means that the smooth curves of spacetime may be emergent approximations, like the gentle slopes of a mountain seen from afar. Up close, the mountain is jagged, and so might be the universe. The elegant differential equations of Einstein describe those slopes perfectly, but they say nothing about the stones beneath them. To understand those stones, we must seek a new language, one that can describe gravity when smoothness no longer applies. At the Planck scale, every known law of physics reaches its breaking point. Quantum mechanics governs the microscopic world, and general relativity governs the cosmic one, but the two refuse to coexist in this tiny frontier. The equations of quantum fields diverge into infinities, while the curvature of spacetime folds upon itself into singularities. It is as though our two greatest maps describe opposite hemispheres of the same planet, but leave the equator blank. That missing region is the domain of quantum gravity, and it is there, at the threshold between the continuous and the discrete, that our next journey begins. The question is no longer how small we can divide, but what replaces division altogether when even the act of measurement collapses into mystery. At the threshold where measurement breaks down, imagination must take the place of observation. The Planck scale cannot be reached by experiment, not because we lack technology, but because the universe itself forbids it. Even the most powerful machines ever conceived, far beyond the energy of any particle accelerator humanity could build, would crumble before approaching such extremes. To compress energy into a region smaller than the Planck length would produce a black hole, sealing all information inside an event horizon. Nature guards her smallest secrets behind that wall. Yet physicists refuse to stop there. Mathematics allows us to explore what observation cannot. By combining the equations of quantum theory with those of general relativity, we can glimpse the strange behavior expected in this forbidden zone. When spacetime is treated as a quantum field, it no longer behaves like a calm, continuous surface. Instead, it flickers and fluctuates. The curvature itself becomes uncertain. Points lose their identity. Distances blur into probability distributions. The universe transforms into a restless geometry in which location, duration, and even dimensionality are no longer absolute. John Wheeler, one of the visionaries of modern gravity, called this imagined realm space-time foam. In his picture, at scales near the Planck length, the fabric of the cosmos boils with fluctuations so intense that it resembles a chaotic ocean of bubbles. Each bubble is a fleeting distortion of geometry, a miniature wormhole or twist of curvature appearing and vanishing almost instantly. Wheeler's insight was profound. If space-time itself can fluctuate, then geometry must be quantized in the same way that light and energy are. The smoothness of the universe would then be an illusion of scale, a grand average of microscopic chaos. Consider how waves in the ocean appear continuous from a distance, though each is built from countless molecules colliding in random motion. The water seems to flow effortlessly, yet every drop within it follows the laws of quantum mechanics. In the same way, space-time may appear as a continuous expanse while being constructed from fundamental excitations far below our power to detect. The Planck scale might not mark an end to structure, but a gateway to a new kind of order, one made not of matter or energy, but of geometry itself. To test such an idea, one must imagine an experiment impossible to perform. Suppose we could observe two particles separated by a distance of 1 Planck length. Quantum mechanics tells us that each particle's position is uncertain by at least that same amount. Their identities would merge, their separation would lose meaning. The concept of between would vanish, replaced by a haze of overlapping probabilities. In that haze, cause and effect may no longer hold. Events could occur without a definite order, connected only by correlations rather than sequence. Reality itself might become non-local, not built from points in space, but from relationships between quantum events. This picture challenges not only physics, but language itself. Our words, before, after, here, there, depend on continuity. Without it, even grammar struggles to describe what happens. When physicists say that space-time becomes non-classical, they mean that our familiar categories no longer apply. The universe at this scale may not be a place in which things happen, but a network of possibilities from which things emerge. Geometry could be an effect rather than a stage, a property arising from patterns of quantum entanglement. In this interpretation, the Planck scale does not represent a smallest piece of space, but the smallest meaningful description of space. Beyond it lies not a deeper layer of structure, but the breakdown of the very idea of structure. Space and time cease to be substances and become bookkeeping devices, convenient ways of summarizing relationships among quantum events. Just as temperature emerges from the average motion of molecules, space-time might emerge from the collective behavior of microscopic quantum processes. If this is true, then the continuum of Einstein's relativity is like the surface of a mirage, perfectly real in its predictions, but not fundamental in its essence. The apparent smoothness of space would arise from the immense number of underlying quantum interactions, just as the warmth of air arises from the chaotic dance of molecules. Continuity, in this sense, would be a large-scale illusion born from the averaging of countless discrete phenomena. The Planck scale would then be not the atom of space, but the threshold where our classical perception dissolves into the quantum substrate beneath. This realization transforms our quest. The goal is no longer to cut space into smaller and smaller pieces, but to understand the rules by which geometry itself comes into being. The question changes from what is space made of to how does space emerge? The limit of divisibility thus becomes a creative frontier, suggesting that reality is not built from things, but from relationships, not from positions, but from patterns. To move forward, we must construct a theory that quantizes not matter within space-time, but space-time itself. And that journey toward the quantum theory of gravity promises to reveal whether the foam of geometry hides true discreteness or whether continuity persists even at the deepest level. At the boundary between what can be known and what can only be imagined, space-time itself becomes a mystery. The familiar equations of physics no longer apply with certainty, and what replaces them is not yet fully understood. Still, from the convergence of quantum theory and relativity, a consistent picture begins to form. A picture in which the smooth fabric of reality gives way to a granular sea of uncertainty. This is the realm where gravity becomes quantum, where geometry itself might come in finite pieces, and where the idea of continuous space may be nothing more than a large-scale illusion. When we examine what happens near this frontier, we find that even the vacuum is not truly empty. Quantum theory insists that fields are never at rest. They fluctuate perpetually, even in the absence of matter or radiation. These fluctuations carry energy, and that energy can, through Einstein's equations, curve spacetime. Thus, the vacuum itself has a shape, constantly shifting on unimaginably small scales. The apparent stillness of space hides an endless dance of virtual particles, appearing and disappearing within times shorter than the Planck time. The deeper we try to probe this void, the more violent and chaotic it becomes, until geometry itself starts to foam and ripple. If one could observe such a domain, it might not look like the infinite blackness of space we know. It might resemble an ever-changing landscape, full of peaks and valleys forming and dissolving faster than any clock could tick. Wormholes could open briefly, connecting distant regions before snapping shut. Tiny black holes could form and evaporate, leaving behind whispers of information. Each Planck-sized bubble would represent a momentary distortion of the universe's geometry, part of a quantum storm that defines the texture of the vacuum itself. This is spacetime foam, the turbulent foundation beneath the calm surface of the cosmos. And yet, despite this chaos, order emerges. On larger scales, those of atoms, planets, and galaxies, these fluctuations average out, producing the smooth continuum described by relativity. The same way that a rough piece of fabric appears soft from afar, spacetime appears perfectly smooth to creatures living within it. The equations of Einstein work because they describe this large-scale behavior with astonishing accuracy. But the perfection of those equations hides their incompleteness. They cannot tell us what happens inside the foam, where curvature becomes quantum and time loses its flow. To explore that hidden realm, physicists attempt to merge the quantum and the gravitational into a single framework. But the task is immense. Quantizing gravity is not as simple as applying the usual tricks of quantum field theory. When the geometry of space becomes uncertain, the background on which all other fields exist vanishes. There is no fixed stage left on which particles can play their roles. Instead, the stage itself becomes part of the performance. This is why traditional methods fail. They rely on the assumption of a smooth spacetime background, the very thing that quantum gravity seeks to replace. Mathematicians have long sought hints of a smallest length through various theoretical routes. Some approaches suggest that spacetime itself might behave like a lattice, with nodes and links representing the tiniest bits of geometry. Others treat it as a web of quantum loops, each loop carrying discrete values of area and volume. These attempts do not merely assume discreteness. They derive it from fundamental principles. When the mathematics of gravity is quantized, it naturally produces spectra of geometric quantities, much like the energy levels of an atom. A surface can have only certain allowed areas. A region can contain only certain allowed volumes. Beneath smooth geometry, there might therefore be a pattern of quantized shapes, woven together by the rules of quantum theory. If this interpretation is correct, then the universe is not infinitely divisible after all. There would be a smallest patch of area, a smallest chunk of volume, and a smallest pulse of time. Between them, reality would not be empty, but undefined, lacking the meaning of between altogether. The continuum we experience would be a macroscopic mirage, created by the collective behavior of countless geometric quanta. It would be as though the cosmos itself were a vast mosaic, its tiles so tiny and numerous that, from our perspective, they blend into seamless curves. But there is another possibility, one that preserves continuity even as it accepts the existence of natural limits. Some theorists argue that the Planck scale does not mark discrete pieces of space, but rather the point at which our current concepts fail. In this view, spacetime remains continuous, but its quantum fluctuations make any attempt to resolve finer detail impossible. The limit of divisibility would then be not a graininess of existence, but a boundary of meaning, a point beyond which the questions we ask cease to correspond to anything real. Just as one cannot meaningfully ask what lies north of the North Pole, one cannot meaningfully ask what lies beneath the Planck scale. Whether the universe is truly discrete or merely appears so remains unknown. Both visions may ultimately converge, for discreteness and continuity could be two aspects of the same underlying reality, revealed differently at different scales. What matters now is that we recognize the Planck scale as nature's frontier, the place where the laws we know are forced to give way to something deeper. It is the horizon of understanding, marking the limit not of space itself, but of our current imagination. From here, the journey moves toward the attempt to cross that boundary in theory, if not in experiment. If we wish to see whether space-time truly consists of discrete quanta, we must learn to describe gravity in quantum language. We must quantize the geometry of existence. That pursuit, the search for the atoms of space-time, will guide the next step in our exploration. The vision of the universe that Albert Einstein gave the world was one of profound elegance. In his equations, space-time is not a stage upon which matter acts, but a living geometry that responds to matter's presence. Where there is mass and energy, space curves. Where space curves, matter moves. The idea seemed simple, but changed everything. It unified gravity and geometry into one continuous dance, replacing invisible forces with the graceful bending of reality itself. The result was a cosmos of seamless continuity, where time flowed without interruption, and where the structure of the universe could be described with infinite smoothness. Imagine an immense sheet stretched tight, like the surface of a calm sea. When a planet sits upon that sheet, it forms a depression. When a moon orbits that planet, it follows the curvature carved into the surface, gliding along paths known as geodesics. In Einstein's general theory of relativity, the sheet is four-dimensional space-time. The geodesics are the straightest possible lines through this curved arena, and gravity is not a force pulling at a distance, but the natural motion of objects following these curves. Nothing is discrete. Every point leads to another. Every direction blends smoothly into the next. Einstein's equations describe this geometry with astonishing precision. The curvature of space-time is encoded in tensors, mathematical objects that link matter and energy to the shape of the universe. The Einstein field equation tells us that the geometry of space-time equals the distribution of mass and energy multiplied by a constant that includes the speed of light and Newton's gravitational constant. It is an equation not of things, but of relationships. Every atom, every star, every beam of light tells space-time how to curve, and space-time tells them how to move. The beauty of this symmetry lies in its continuity. There are no jumps, no smallest units, no interruptions in the fabric. In Einstein's world, smoothness is not just a feature, it is a necessity. The mathematics of differential geometry, which underlies relativity, assumes that one can zoom in endlessly and still find the same structure. Curvature, for example, is defined through infinitesimal changes in direction, and those changes are meaningful only in a continuum. If space-time were made of discrete chunks, the very calculus that forms the heart of the theory would collapse. To compute curvature, one must be able to take limits as distances shrink towards zero. And in relativity, zero is not a forbidden word. It is the foundation of the entire edifice. This smooth geometry describes every gravitational phenomenon we have ever measured. The bending of light near the sun, the precise orbit of Mercury, the expansion of the universe itself, all align perfectly with Einstein's predictions. Even the ripples of space-time detected by observatories such as LIGO, caused by colliding black holes billions of light-years away, behave exactly as continuous waves should. The theory has passed every test with flawless accuracy. It works so well that one could almost forget how radical its assumptions are. And yet, beneath its perfection lies a subtle tension. Einstein's equations are classical, meaning they describe a universe where quantities like position, momentum, and curvature are exact and continuous. But quantum mechanics, discovered only a few years after Einstein's triumph, shattered that picture. It revealed a world of probabilities and uncertainties, where nothing can be perfectly smooth or perfectly known. The universe of the very small does not obey the rules of the continuous, but the logic of the discrete. It trades determinism for chance and replaces continuous fields with quantized excitations. Einstein himself resisted this new paradigm. He believed that the universe was ultimately continuous and that the apparent randomness of quantum events was the result of an incomplete description. He famously declared that God does not play dice with the cosmos, but the experiments that followed proved otherwise. Quantum behavior was not an illusion. It was a fundamental feature of nature. At the smallest scales, energy, angular momentum, and even light come in discrete packets. If everything else in the universe is quantized, why should spacetime be different? Still, for all its paradoxes, Einstein's smooth universe remains unmatched in its explanatory power. Its predictions hold across cosmic distances and extreme conditions. The GPS signals guiding airplanes and phones depend on its precision. The bending of starlight around distant galaxies reveals invisible masses of dark matter using the geometry he described. On these scales, discreteness, if it exists, leaves no trace. The continuum reigns supreme, as though the universe itself were a flawless manifold extending without end. But when we push the theory too far, its serenity falters. At the heart of a black hole, curvature grows without limit, collapsing into a singularity where density becomes infinite and the equations of relativity lose meaning. The same happens when we trace the expansion of the universe backward in time to the Big Bang. There too, the equations predict an infinite curvature, an edge to space and time where smoothness cannot survive. These singularities are the scars that mark the breakdown of the continuum. They are signs that Einstein's fabric, for all its elegance, is incomplete. To heal those infinities, we must bring quantum mechanics into the story. Only a quantum theory of gravity can reveal what happens where curvature becomes infinite and where distances reach the Planck scale. If spacetime is indeed composed of discrete elements, then those singularities might not be infinities at all, but places where the smooth description gives way to a granular one. The fabric may tear, but beneath the tear lies a pattern. In the next stage of our exploration, we will follow this thread. We will see how physicists have tried to merge the smooth geometry of Einstein with the quantized world of Planck, and how their efforts have led to the idea that spacetime itself may be made of atoms of geometry. The question is not whether Einstein was wrong, but how far his smooth universe can be stretched before it dissolves into its quantum foundation. Einstein once said that his greatest joy came from the harmony he found in the universe's mathematical order. That harmony depended on the idea that space and time form a single, unbroken continuum. It was a concept that united everything, from the fall of an apple to the motion of galaxies, under one geometry. To Einstein, spacetime was the stage upon which the universe performed its play, and that stage itself was as real as the actors upon it. The geometry of the cosmos was not an illusion or a convenience, it was existence itself. The power of this vision lies in how naturally it explains gravity. For centuries, Newton's theory described gravity as an invisible force pulling objects together. Einstein replaced that pull with curvature. A massive object, such as the Earth, bends space-time around it. Other objects, like the Moon, follow the straightest possible paths within that curved geometry. From this perspective, orbits are not acts of attraction, but the natural motion of bodies through a warped landscape. The Moon is not pulled by the Earth's gravity. It simply moves straight through a curved space-time, looping endlessly because space itself bends back on itself. This elegant picture extends to the universe as a whole. On the largest scales, the same geometry that explains falling apples and orbiting planets describes the expansion of the cosmos. The general theory of relativity tells us that the universe can stretch or contract depending on its energy content. Einstein's equations predict how galaxies move through that expanding geometry, how light from distant stars is stretched into longer wavelengths, and how massive clusters act as cosmic lenses that bend the paths of photons traveling across billions of light years. Everywhere we look, the smooth fabric of space-time behaves exactly as the theory demands. To describe this mathematically, Einstein built on the tools of differential geometry developed by Riemann in the 19th century. In this framework, curvature is not a mysterious force, but a precise mathematical property of space. At every point, one can define tensors, objects that measure how vectors change as they move across curved surfaces. The Einstein field equation balances this curvature against the energy and momentum of matter. It is a relationship of exquisite symmetry, one that can describe both the collapse of stars and the birth of universes. The theory's predictions have been tested to extraordinary precision, from the bending of light during solar eclipses to the orbit of pulsars locked in gravitational embrace. Every test confirms the same truth. Space-time behaves as a smooth, continuous manifold. But this perfection is deceptive. The mathematics of general relativity assumes that one can always zoom in on smaller and smaller regions of space and time without encountering limits. In practice, this means that the geometry must remain well-defined no matter how closely one examines it. Yet the universe may not agree. When we approach the singularity inside a black hole, the curvature grows without bound. The very quantities that define geometry, distance, area, volume, lose meaning. Time itself ceases to flow in any normal sense. At that point, the smoothness at the heart of Einstein's theory collapses into uncertainty. The same problem appears when we look backward toward the beginning of the cosmos. The equations that describe the expansion of the universe can be traced to a single moment when all distances shrink to zero and densities become infinite. But infinities in physics are warnings. They signal that the theory has been pushed beyond its range of validity. Einstein's smooth universe, for all its elegance, cannot describe what happens at these edges. It can predict the motion of galaxies and the collapse of stars, but it falters at the boundaries of creation and destruction. The smooth fabric tears, revealing a hole that classical physics cannot mend. Physicists have long suspected that the missing ingredient is quantum mechanics. Quantum theory governs the behavior of matter and energy on the smallest scales, introducing a natural granularity to reality. Photons, electrons, and all other particles exist in discrete states, and their interactions occur in quantized steps. If matter and energy are quantized, then the geometry that binds them might be quantized as well. But Einstein's equations resist such treatment. When we try to apply quantum methods to gravity, the results explode into infinities. The very continuity that gives relativity its power becomes the obstacle preventing it from merging with the quantum world. This conflict defines modern theoretical physics. On one side stands Einstein's vision of a smooth continuum, where curvature flows without interruption. On the other stands the quantum world, full of jumps, probabilities, and discrete transitions. Each is complete in its own domain, yet they cannot both be right in the same place. Somewhere between the curvature of black holes and the fluctuations of quantum fields, the two descriptions must meet. But at that meeting point, the Planck scale, our current mathematics fails. Einstein himself sensed this incompleteness. He spent the later decades of his life searching for a unified field theory, a single framework that would connect gravity with electromagnetism and perhaps with all other forces. Though he never succeeded, his pursuit left behind a profound question. Is space-time itself continuous, or is it woven from something deeper? To answer that question, we must go beyond relativity without abandoning its insights. We must quantize the very geometry of existence. If Einstein's equations describe the surface of the ocean, then quantum gravity seeks to reveal the waves beneath it. Somewhere in that unseen realm, the smooth flow of space-time might emerge from discrete interactions, the same way a continuous melody arises from the vibrations of individual strings. The search for that underlying structure defines the next frontier in physics. Einstein's smooth universe is a masterpiece of consistency, yet every masterpiece conceals the edges of its canvas. To appreciate its power, we must also recognize its boundaries. The general theory of relativity is built upon a geometric foundation that treats space-time as a continuous manifold, an unbroken expanse that can be described everywhere and at every scale. It assumes that infinitesimal distances and infinitesimal durations can be defined without limit. This assumption has guided a century of discoveries, from the bending of light to the detection of gravitational waves. But at the deepest levels, it may no longer hold. To see why, imagine tracing the history of the universe backward in time. As we go back, galaxies draw closer, temperatures rise, and matter becomes denser. Eventually, we reach a point where density and curvature become infinite, the singularity of the Big Bang. At that moment, the equations of general relativity produce meaningless infinities. They tell us that the entire universe was once contained in zero volume and infinite energy, a mathematical impossibility. The same singularity appears inside black holes, where the smooth geometry folds in on itself. The theory that so elegantly describes planets and stars cannot describe the very extremes it predicts. This failure is not just a mathematical quirk, it is a clue. It tells us that the smooth continuum of spacetime may be only an approximation, a large-scale description that breaks down at the smallest scales. In the same way that fluid dynamics ceases to apply when we look closely enough to see individual molecules, general relativity may cease to apply when we look closely enough to see the quantum structure beneath spacetime. The challenge is that no experiment can yet reach such scales. We can see the ripples of spacetime from colliding black holes, but not the granularity that might lie beneath those waves. Still, mathematics can reach where instruments cannot. The search for a quantum theory of gravity begins by asking what would happen if spacetime itself were quantized. Could we define atoms of geometry, discrete units of area and volume that add up to form the smooth continuum we observe? In this vision, space would no longer be a background, but a dynamic network of relationships, each link representing a quantum of curvature. At large scales, the links would blend together, creating the illusion of smoothness. At small scales, they would reveal their discrete nature, much as pixels reveal themselves when a digital image is magnified. This idea does not diminish Einstein's insight, it deepens it. His equations describe how matter and energy shape geometry, and how geometry in turn shapes motion. In a quantum theory of gravity, the same principle holds, but geometry itself becomes quantized. Space and time would not merely bend, they would fluctuate, vibrate, and exchange quanta of curvature. The fabric of reality would not be continuous cloth, but woven threads, each carrying a finite amount of geometric information. Einstein might have resisted such an idea. To him, the strength of physics lay in its continuity. He believed that smooth fields and continuous symmetries were the natural language of the universe. The discreteness introduced by quantum mechanics felt to him like a temporary patch on a deeper, more unified reality. Yet history has shown that nature often prefers discreteness. Light comes in photons, energy levels in atoms are quantized, and even electric charge exists only in multiples of a fundamental unit. It would be no great surprise if space and time followed the same rule. In many ways, general relativity still serves as our map of the macroscopic cosmos, while quantum mechanics charts the microscopic one. The boundary between them is not sharp but hidden, buried at the Planck scale. Einstein's smooth manifold may be like the Earth's surface, as seen from an airplane, beautifully continuous until one descends low enough to see mountains, rivers, and grains of sand. The structure of spacetime could be the same, appearing continuous only because our perspective is too coarse to see its granularity. And yet, the beauty of Einstein's theory endures. Even if it is not the ultimate truth, it remains one of the most precise descriptions of reality ever achieved. It captures the curvature of the cosmos with mathematical grace, predicting phenomena that seemed impossible when first proposed. Time dilation, gravitational lensing, the expansion of space, all flow naturally from its geometry. In the vast theatre of the universe, it is still the most faithful script we possess. The next step in our journey is to see how this script can be rewritten without losing its poetry. To understand the discrete, we must first learn to quantize the smooth. Physicists have spent decades attempting to do just that, giving birth to competing visions of quantum gravity. Some picture spacetime as a network of loops, others as vibrating strings. Each offers a glimpse of how the continuous fabric Einstein imagined might arise from deeper, quantized structures. It is at this juncture, between the serene continuum of general relativity and the restless granularity of quantum mechanics, that modern physics stands poised. The question is not whether Einstein's smooth universe is wrong, but how it transforms when viewed through the lens of quantum reality. Perhaps the smoothness is not lost, but revealed as an emergent illusion, the visible harmony of countless microscopic notes. The melody of spacetime may be continuous to our ears, yet built from the rhythm of discrete quanta beneath. And so, our journey continues, from the infinite curves of Einstein's geometry to the quest for the smallest loops and threads that might compose them. The next chapter leads us into that frontier where physicists seek the building blocks of spacetime itself and the long-awaited bridge between the continuous and the discrete. The dream of unifying the smooth curves of general relativity with the quantum grain of matter has haunted physics for nearly a century. At first, the task seemed simple enough. If electromagnetic waves could be quantized into photons, why not do the same for gravity? But the attempt to quantize Einstein's field equations has proven far more treacherous than anyone expected. The closer we look, the more gravity resists the logic that governs the rest of physics. The reason lies in its very nature. Gravity is not a force that lives within spacetime. It is the shape of spacetime itself. To quantize it, we must quantize geometry, and that is a problem unlike any other. When physicists first tried to treat gravity as another field, they used the same tools that worked for electromagnetism. They imagined a particle that carries the gravitational interaction, just as photons carry the electromagnetic one. This hypothetical particle became known as the graviton. If spacetime could be thought of as a smooth background, then the graviton would be a small vibration within it, ripples of curvature propagating through emptiness. The mathematics worked beautifully at first, predicting gravitational waves and small fluctuations in flat spacetime. But as soon as one pushed beyond these simple cases, infinities began to appear, uncountable divergences that no trick of renormalization could tame. Gravity refused to fit the quantum mold. The problem is that the gravitational field is inseparable from spacetime itself. When one quantizes gravity, one quantizes the very coordinates used to measure distances and times. The stage of physics becomes part of the play, and there is no external backdrop left to define what is happening. It is as if one were trying to paint a canvas that keeps changing shape beneath the brush. Without a fixed geometry, the ordinary methods of quantum field theory lose their footing. The mathematics collapses into infinite uncertainty, suggesting that something more fundamental must replace the smooth continuum. This realization gave birth to a new generation of ideas. Attempts not to quantize gravity on a background, but to build spacetime itself out of quantum principles. One of the most ambitious of these is loop quantum gravity, often abbreviated as LQG. Instead of treating spacetime as continuous, it describes it as a network of finite loops, each carrying a quantum of area or volume. In this theory, the geometry of the universe is woven from threads of energy, forming an immense and dynamic web. The nodes of this web represent points of intersection where loops connect, while the links represent quantized relationships of curvature. At large scales, the web becomes so dense that it appears smooth, just as a woven fabric looks continuous to the naked eye. Loop quantum gravity predicts that space itself is quantized. Areas and volumes cannot take arbitrary values, but come in discrete steps determined by the Planck scale. A surface, for example, might have an area that is an integer multiple of the Planck area, which is about 10 to the power of -70 square meters. Below that, the concept of area simply ceases to have meaning. Similarly, the volume of a region cannot shrink continuously to zero, but is composed of finite quanta. These predictions suggest that the infinities of relativity, those that occur at the centers of black holes or at the birth of the universe, might be resolved naturally. Instead of singularities, there would be finite regions where geometry reaches its smallest possible unit. In this picture, space-time is no longer a smooth ocean, but a sea of quantum foam frozen into a crystalline lattice of probability. The curvature of space corresponds to the interconnections of loops, and the flow of time arises from their evolution. The mathematics behind this idea uses structures called spin networks. Each node of a spin network carries quantum numbers representing the smallest bits of geometry. As these networks evolve, they form spin foams, four-dimensional analogues describing how the fabric of space changes through time. To the human eye, the result would appear continuous, but at the fundamental level, it would be as pixelated as a digital image. What makes this vision so compelling is that it does not need a background spacetime to exist. It builds spacetime from the bottom up. The geometry of the universe becomes an emergent phenomenon, born from relationships among quantum variables. There is no emptiness waiting to be filled, no pre-existing coordinate system. The structure of space is the structure of the quantum network itself. This means that the very concept of location becomes relational. There is no place in isolation, only connections. The beauty of loop quantum gravity lies in how it preserves Einstein's geometric insight while respecting the granularity of quantum mechanics. It keeps the essence of curvature and geodesics, but replaces the continuous manifold with a discrete web of quantum geometry. The result is a picture of the cosmos where smoothness is not fundamental, but emergent. At our scale, the loops are so densely packed that space-time behaves like a continuum. But if one could shrink to the Planck scale, one would see the structure beneath, a tapestry of interwoven loops, each vibrating with the energy of existence itself. This is not the only path toward quantum gravity. Another contender takes a very different route. Instead of replacing space-time with loops, it replaces point particles with tiny, one-dimensional strings. These strings vibrate in multiple dimensions, and each vibration corresponds to a different particle. In string theory, the graviton arises naturally as one of the vibrational modes. The geometry of space-time is still continuous, but the strings cannot probe below a certain length, providing a natural cutoff that prevents infinities. In this way, string theory preserves the continuum while building discreteness into the physics of measurement itself. Both approaches, loop quantum gravity and string theory, confront the same mystery from opposite directions. One makes space-time discrete to recover smoothness. The other keeps space-time continuous but imposes a smallest possible length. Both suggest that the Planck scale marks a fundamental limit. It is there that the old distinction between discrete and continuous begins to blur. The universe may be both at once, discrete at its core, but smooth in its manifestation. At the heart of the search for quantum gravity lies a profound realization. The question is not only what space-time is made of, but whether it is made of anything at all. In general relativity, geometry is everything. It defines how matter moves and how energy shapes the universe. In quantum mechanics, geometry is nothing. It is the fixed stage on which particles and fields perform their probabilistic dance. To unite these two visions, we must find a description where geometry itself becomes quantum, where the very notion of distance and duration depends on the state of the universe. This shift changes the way we think about reality. Space and time are no longer the background. They are part of the cast. loop quantum gravity offers one path toward this vision. In its equations, space is represented by networks of connections rather than by coordinates. These connections carry values called spins, which determine the smallest measurable units of area and volume. A spin network is not drawn upon a pre-existing space. It is space. The links and nodes of the network define adjacency, direction, and dimension. When a network evolves, it forms a spin foam, describing the flow of geometry through what we call time. The image is almost organic, a web of quantum threads constantly rearranging itself, creating and annihilating bits of space as it unfolds. In this framework, the familiar continuum emerges as a kind of statistical illusion. Just as a continuous melody arises from discrete vibrations of air, space-time emerges from the collective behavior of these loops. Every interaction in the universe, every collision, decay, and fluctuation is encoded in changes within this web. The smooth geometry of Einstein's relativity is what the world looks like when you average over countless such events. The loops themselves are far too small and too fast to observe directly. They form the invisible scaffolding beneath all existence, the quiet architecture of reality. Loop quantum gravity also offers a way to resolve the paradoxes that plague classical relativity. Take the singularity at the center of a black hole, where density and curvature grow without limit. In the loop picture, space-time cannot collapse into infinite curvature because area and volume are quantized. There is a smallest possible volume, and once matter compresses to that point, the geometry resists further collapse. Some models even suggest that instead of a singularity, a black hole may contain a bridge to another region of space-time, a kind of quantum bounce. The same idea might apply to the birth of the universe. Instead of beginning in an infinite singularity, the cosmos could have rebounded from a previous phase of contraction. The Big Bang would then be a big bounce, where one universe gives birth to another. But loop quantum gravity is not without challenges. It provides a beautiful mathematical framework, yet connecting it to observable reality remains difficult. Predicting measurable consequences from such a tiny scale is nearly impossible with current technology. The theory's equations are abstract, and while they yield discrete spectra for geometric quantities, testing those predictions requires energies trillions of times beyond our reach. Still, the theory's internal consistency and its ability to remove singularities make it one of the most compelling candidates for a quantum theory of gravity. String theory approaches the same puzzle from another angle. Instead of replacing points with loops of geometry, it replaces them with tiny vibrating strings. These strings are unimaginably small, roughly the Planck length in size, and their vibrations determine the properties of particles. A single string can vibrate in countless modes. One mode appears as an electron, another as a quark, another as a graviton. The diversity of particles in nature emerges from the harmonics of these strings. The idea transforms matter, energy, and even space-time into manifestations of a deeper underlying unity. Unlike loop quantum gravity, string theory preserves the continuum. Space-time remains smooth, but strings cannot probe distances smaller than their own size, effectively preventing the infinities that plague point-particle theories. This built-in limit acts as a natural regulator. When two strings collide, they smear out their interactions over a finite region, avoiding the singularities that appear when point particles meet. Thus, string theory brings a kind of soft discreteness to a continuous framework. It allows infinite divisibility in principle, but not in practice. One of string theory's most striking predictions is that the universe may have more dimensions than we perceive. In order for the mathematics to remain consistent, the theory requires 10 spatial dimensions and 1 of time. The extra dimensions are thought to be compactified, curled up so tightly that they are invisible to us, much like the thickness of a thread is invisible when viewed from afar. The shape of these hidden dimensions determines the physical properties of our universe. In that sense, the geometry of the unseen directly shapes the particles and forces we observe. Within this framework, gravity arises naturally. The graviton, the particle that mediates gravitational interactions, emerges as one of the string's vibrational modes. But the deeper significance of string theory lies in what it suggests about the nature of space-time itself. It implies that the smooth geometry of relativity is not fundamental, but emergent from the dynamics of strings. The strings themselves exist in a higher dimensional space called the bulk, and their interactions give rise to the lower dimensional reality we inhabit. This idea leads to one of the most remarkable insights in modern physics, the holographic principle. According to this principle, everything that happens within a volume of space can be described by information encoded on its boundary, much like a three-dimensional image can be represented on a two-dimensional hologram. In certain versions of string theory, a continuous curved spacetime emerges from the behavior of quantum fields living on a lower dimensional surface. The universe, in this view, might be a projection of more fundamental degrees of freedom existing elsewhere. Both loop quantum gravity and string theory offer glimpses of a universe built from discrete informational building blocks. One constructs geometry from loops, the other weaves it from vibrating strings. Both dissolve the classical distinction between space, time, and matter. Each suggests that what we call the fabric of reality may be more like a code, an intricate pattern of relationships rather than a continuous expanse. The challenge now is to determine which, if either, of these visions is true. Each captures part of the truth, yet neither has revealed the full picture. The next step lies in asking whether these quanta of geometry, these atoms of spacetime, can ever be detected. Can the granularity of the universe leave a trace, a whisper, that we might one day hear? The question of whether spacetime is made of discrete atoms is no longer philosophical. It is a challenge to our instruments, our mathematics, and our imagination. Both loop quantum gravity and string theory suggest that beneath the smoothness of Einstein's geometry lies a substructure, a kind of microscopic architecture of reality. But how could we ever prove it? The Planck scale is so small that even the most powerful experiments humanity can build fall short by orders of magnitude. To detect the grain of spacetime directly would require energies far greater than anything achievable by particle accelerators, far beyond what even cosmic rays provide. Yet physicists are patient. Where direct detection fails, indirect evidence may still whisper through the noise of the cosmos. If space and time are indeed discrete, that discreteness might reveal itself, not in what we see, but in how things move. Consider light traveling across the vast distances of the universe. In a perfectly continuous spacetime, all photons, regardless of their energy, should move at the same speed, the speed of light. But if spacetime has an underlying graininess, higher energy photons might interact differently with that structure, producing tiny differences in arrival times. Observing these delays in light from distant gamma-ray bursts could, in principle, reveal hints of spacetime discreteness. Astronomers have searched for such effects using satellites like the Fermi Gamma Ray Space Telescope. So far, no measurable dispersion has been found, but the search continues, reaching further across the universe and into the faintest echoes of the Big Bang. There are other ways to listen for spacetime's hidden rhythm. Gravitational waves, those ripples in spacetime first detected by LIGO, may carry subtle fingerprints of quantization. If the fabric through which they travel is made of discrete loops or strings, then at sufficiently high frequencies, those waves might scatter, blur, or decohere. Detecting such distortions would require instruments far beyond our current precision, but the idea itself is sound. Even a single confirmed anomaly could point to the existence of a quantum grain beneath the continuum. Loop quantum gravity predicts specific quantum properties of black holes that might one day be observable. According to the theory, The surface area of a black hole's event horizon is quantized, increasing or decreasing only in discrete steps when matter falls in or radiation escapes. This leads to a spectrum of possible black hole masses, rather than a continuous range. Some physicists speculate that as a black hole evaporates through Hawking radiation, these steps might leave tiny imprints in the emitted energy, patterns that could, in principle, be detected. The mathematics is tantalizing, but the signals would be extraordinarily faint. Detecting them might require instruments sensitive enough to measure single quanta of spacetime itself. String theory, too, offers potential clues. The extra dimensions predicted by the theory might produce observable effects in high-energy collisions, such as the production of microscopic black holes or deviations from the expected behavior of gravity at short distances. Experiments have searched for such deviations using delicate torsion balances and particle accelerators. None have yet appeared, but the constraints these experiments impose help refine the theory. Every null result narrows the field, guiding physicists closer to the truth. The challenge of finding evidence for spacetime discreteness goes beyond mere technology. It forces us to question what evidence even means. If spacetime itself defines the framework of measurement, how can we measure its internal structure? We are like fish trying to detect the texture of the water in which we swim. Our rulers and clocks are part of the very fabric we seek to probe. To study the grain of spacetime, we must find ways to make it reveal itself indirectly, through its influence on the behavior of matter, light, and gravity. There are hints, faint and scattered, that may one day converge. Some researchers have proposed that quantum noise, tiny fluctuations observed in highly sensitive interferometers, could be the echo of spacetime's discreteness. Experiments like the Fermilab holometer have sought to detect such quantum jitter in the positions of mirrors, attempting to measure the smallest possible trembling of spacetime itself. The results so far show no sign of a discrete structure, but they have pushed the limits of precision closer to the Planck scale than ever before. Each failure is also a success, for it defines the boundary of what spacetime allows us to see. As theories advance and experiments refine, a deeper philosophical realization emerges. The universe may be neither purely discrete nor purely continuous. Instead, these two pictures might be complementary, describing the same reality from different perspectives. To us, spacetime appears continuous because we observe it from far above the Planck scale, just as a digital image appears smooth when viewed from afar. But up close, at scales far beyond our current reach, the same smoothness might dissolve into quantum granularity. Continuity would then be an emergent property, a kind of statistical illusion born from the behavior of countless spacetime quanta. This insight reshapes our understanding of existence itself. If spacetime is composed of discrete units, then every moment of reality is finite, every distance countable, every duration composed of indivisible ticks. Yet those quanta, when woven together, create the infinite symphony of the cosmos, a universe that expands, evolves, and dreams within its own geometry. The smoothness we see is the melody, the discreteness beneath it, the notes. For now, we remain suspended between these two visions. Einstein's continuum and Planck's discreteness coexist in uneasy harmony, awaiting the theory that will reveal how one becomes the other. Whether the fabric of the universe is woven from loops, strings, or something yet unimagined, the search for spacetime's atoms continues, not merely as a quest for knowledge but as an act of wonder. To ask if spacetime is discrete or continuous is to ask how the universe writes its own story, in an unbroken flow, or in a series of quantum beats that together compose the rhythm of existence. The deepest questions in physics are often not those we can answer, but those that defy every experiment we design. The nature of spacetime's fabric, whether it is continuous or made of discrete quanta, belongs to that category of mysteries that stand just beyond our reach. Theories have advanced, mathematics has evolved, and imagination has soared, yet evidence remains stubbornly silent. The universe has hidden its smallest scales beneath a veil that even our most powerful instruments cannot pierce. But silence does not mean emptiness. It may simply mean that the clues are subtle, scattered across the cosmos, waiting to be read in the faintest whispers of energy, light, and gravity. Physicists have always been hunters of limits. The more precisely we measure, the more clearly we define where our knowledge ends. Today, that limit lies roughly 15 orders of magnitude above the Planck scale. The Large Hadron Collider can probe distances as small as about 10 to the power of -20 meters, an achievement beyond imagination compared to human history, yet still trillions of times larger than the scale where spacetime's grain might appear. It is like trying to detect the texture of paper using a telescope. We can see only smoothness, though we suspect roughness beneath. The absence of direct evidence does not mean the idea of spacetime discreteness lacks merit. Nature often hides its secrets in ways that reveal themselves only through indirect effects. Just as the existence of atoms was once inferred from patterns in heat and pressure rather than seen directly, so too might the atoms of spacetime reveal themselves through the behavior of the cosmos. The task, then, is to look not for the granules themselves, but for their influence on the continuous world we observe. One of the most promising places to search is in the light that has traveled the farthest. High-energy gamma rays from distant cosmic explosions, known as gamma-ray bursts, offer a natural laboratory for testing the smoothness of spacetime. These bursts are unimaginably bright, releasing in a few seconds more energy than the sun emits in billions of years. As the photons journey across billions of light-years, even the tiniest irregularities in the fabric of spacetime could alter their path. If spacetime were granular, higher energy photons might interact with its structure slightly differently, causing them to arrive at Earth a few moments before or after their lower energy counterparts. The Fermi Gamma Ray Space Telescope has been searching for precisely such effects. Over the years, it has recorded hundreds of gamma ray bursts, some from galaxies billions of light-years away. Each burst serves as a test of spacetime's uniformity. So far, the data reveal no measurable dispersion in arrival times that cannot be explained by other astrophysical processes. If spacetime has a grain, its texture must be far finer than even the most sensitive observations can detect. The universe, for all practical purposes, still appears perfectly smooth. Yet physicists remain undeterred. They have learned from history that nature often hides its transitions beneath layers of scale. When Max Planck first introduced the idea of energy quanta, no one could detect them directly. It took decades of indirect measurements, photoelectric effects, spectral lines, and blackbody radiation curves before the quantum structure of energy became undeniable. The same may be true for spacetime. The signs of discreteness might already be imprinted across the universe, faint but persistent, awaiting interpretation. One of the next frontiers lies in the study of gravitational waves, the ripples in spacetime caused by massive cosmic events like the collision of black holes. Detected for the first time in the year 2015 by the Laser Interferometer Gravitational Wave Observatory, these waves confirmed Einstein's century-old prediction. But while they behave like continuous oscillations in a smooth medium, it is possible that at very high frequencies, they could reveal irregularities, tiny distortions that betray an underlying quantum structure. In principle, if spacetime were granular, those ripples might scatter or lose coherence, producing noise patterns invisible in a purely continuous model. Detecting such subtle effects would require sensitivity far beyond the current limits of LIGO or Virgo, yet the path forward is clear. Each generation of detectors pushes the boundary closer to the realm where discreteness might show itself. Other experiments have sought the grain of spacetime through the most delicate of means. The holometer experiment at Fermilab tried to measure quantum jitter in spacetime itself, random fluctuations that might occur if space is composed of discrete informational units. The setup used two precisely aligned interferometers to detect correlated noise that could not be explained by classical vibrations or instrument error. The idea was that if space-time were truly made of quantum pixels, those pixels might produce a kind of background hum, a universal quantum fuzz. The results, however, showed no such signal. The cosmos, to the precision of our instruments, remained silent, but null results are still results. They refine our understanding of what the universe is not. They tell us how subtle the quantum grain of reality must be and how gracefully the continuum emerges from whatever lies beneath. The absence of evidence becomes its own form of guidance, steering theory toward the regions where truth may yet hide. If discreteness exists, it may not manifest as irregularities in motion or noise, but as constraints on how much information the universe can hold. The holographic principle, born from studies of black holes, suggests that there is a finite number of bits that can describe any region of space. A black hole's entropy is proportional to the area of its event horizon, not its volume, hinting that the universe's information content is fundamentally discrete. If that principle holds universally, then space-time itself must be quantized at the level of information. The granularity would not appear in motion or light, but in the very counting of possible states. Thus, the search for evidence becomes as much philosophical as experimental. We are not merely asking whether space-time is smooth or grainy, but what kind of reality produces such perfect continuity. If the universe is discrete, then our instruments may never see its atoms directly. They will see only the echoes of limitation, the faint boundaries of what can be known. If it is continuous, then its perfection must somehow arise from infinite complexity without contradiction. Either answer is extraordinary. For now, the evidence we seek remains hidden in the silence of space-time itself. Every signal we record, every wave and photon we capture, tells the same story. Smoothness reigns supreme. Yet the theories insist that beneath that calm surface lies a restless quantum sea. To bridge the gap between them, we must look not just outward into the cosmos, but inward into the logic of nature's code. The next step is to explore that code itself, the information that might define the structure of reality more deeply than matter or geometry. The more we search for the granularity of space-time, the more the universe seems to conspire to hide it. Every experiment confirms the precision of Einstein's equations, as if nature insists that the continuum is all there is. Gravitational waves ripple flawlessly through space, light bends and redshifts exactly as predicted, and the orbits of planets and pulsars follow the smooth geodesics carved by mass and energy. To all our senses, space-time behaves as a continuous, perfectly elastic fabric. And yet, our deepest theories whisper that this smoothness cannot be the whole truth. Physicists have learned to read between the equations, searching for the subtle places where the continuum begins to strain. One such place lies in the behavior of quantum fields at extremely high energies. According to quantum field theory, every point in space contains a set of fluctuating fields that constantly exchange virtual particles. The energy of these fluctuations should be infinite if space is truly continuous, since an infinite number of modes can exist at arbitrarily small scales. Yet infinity cannot be measured, and nature clearly avoids it. The fact that the universe's vacuum energy is finite, though enormous, suggests that there is a cutoff somewhere, a smallest possible wavelength, below which the fields no longer vibrate. That cutoff may be the Planck scale, the first hint of discreteness hidden in the mathematics of the quantum vacuum. Even so, the challenge remains. How can we see something that cannot be seen? One idea comes from studying the most energetic particles ever observed, cosmic rays that strike the Earth's atmosphere with energies millions of times greater than those produced by the Large Hadron Collider. If space-time were granular, these particles might interact with its structure, losing energy or scattering in ways that deviate from standard physics. But the observed distribution of cosmic ray energies matches the predictions of continuous space-time perfectly. No anomalies, no irregularities, just the same smooth geometry extending from the subatomic to the cosmic scale. This persistence of smoothness has led some to wonder if our search for discreteness might be misguided. Perhaps space-time is continuous after all, and the Planck length is not a brick in the wall, but a limit of meaning. Beyond it, the concepts of distance and time may simply cease to apply, not because reality stops, but because our language does. In that case, the question, is space-time discrete, would be like asking, what lies north of the North Pole? A question formed by stretching a concept beyond where it belongs. Still, other clues tempt us to think otherwise. The holographic principle, derived from the thermodynamics of black holes, tells us that the amount of information that can fit into a given region of space is finite and proportional to its surface area, not its volume. That limit implies a discrete information density, a finite number of fundamental bits per unit area. In that sense, even if space-time feels smooth, it may behave as though each patch of surface holds a finite number of possible states. Like the pixels of a digital image, these informational units are not visible individually, but they set the resolution of the universe. The continuum we see is the illusion of infinite resolution, when in truth the cosmic screen has limits. The black hole is perhaps the clearest window into this mystery. When matter falls into a black hole, all the information about its composition, its arrangement of particles, fields, and forces seems to vanish behind the event horizon. Yet quantum mechanics forbids information loss. Stephen Hawking's work on black hole radiation showed that black holes emit faint thermal radiation, meaning they can evaporate over immense timescales. This process leads to a paradox. If information cannot be destroyed, where does it go when the black hole disappears? The resolution of that paradox appears to depend on the discreteness of space-time itself. If the surface area of the black hole's horizon is quantized, then its entropy, proportional to that area, must also be quantized. Each step of evaporation would correspond to the loss of a specific number of bits, encoded in the geometry of the horizon. Information would not vanish, but would be released gradually in the radiation, hidden within correlations too subtle for current instruments to detect. In this view, spacetime's discreteness provides a natural bookkeeping system, ensuring that information is conserved even as geometry changes. There are also hints in the structure of quantum entanglement, the strange connection that allows particles separated by vast distances to share information instantaneously. In some theoretical models, entanglement is not a feature of spacetime. It is what creates spacetime. The web of entangled quantum bits might form the scaffolding from which geometry emerges. If this idea is correct, then discreteness is not a property of space, but of information itself. The atoms of spacetime are not tiny physical objects, they are relationships between quantum states. The search for evidence thus becomes a search for patterns in information. Some physicists are turning to cosmology for answers, studying the afterglow of the Big Bang, known as the cosmic microwave background. Tiny fluctuations in that ancient light may carry imprints of quantum gravity processes from the earliest moments of the universe. If spacetime was discrete, the distribution of these fluctuations could deviate slightly from what a purely continuous model predicts. So far, the data from satellites like Planck and WMAP have shown remarkable consistency with smooth inflationary models. But again, the precision of our instruments may not yet be enough. Despite the lack of confirmation, the quest itself has become a defining pursuit of modern physics. It forces scientists to refine their instruments, deepen their mathematics, and rethink the very meaning of observation. Each failed attempt sharpens the next. Each null result strengthens the discipline of curiosity. It is as if the universe is testing our patience, revealing its secrets not to those who demand answers, but to those who are willing to ask better questions. Perhaps one day, the evidence will arrive not from a distant telescope or a collider, but from a new kind of experiment, one that measures information directly rather than energy or position. Until then, we remain in the domain of inference, where every photon, every vibration, and every equation becomes a clue. The continuum still holds, but the possibility of its breakdown keeps science alive. To stand at the edge of knowledge is to feel both awe and frustration. The universe reveals itself with generosity, but only so far. Beyond that, it hides its foundations behind veils of scale and energy that no experiment can yet penetrate. We can describe the evolution of galaxies, the fusion of stars, the interactions of subatomic particles, but when we ask what space-time itself is made of, the answers turn to shadows. The evidence we seek may be all around us, encoded in the behavior of the cosmos, but so faint and so subtle that our instruments have not yet learned to listen. Still, nature leaves hints. One of those hints may lie in the phenomenon of quantum decoherence. In quantum mechanics, particles exist in superpositions, states that are both this and that until they are observed. But when many particles interact, that delicate quantum coherence tends to disappear, replaced by the familiar definiteness of the classical world. Some physicists wonder whether space-time discreteness could play a role in that transition. If space itself is composed of finite units, perhaps those units act as a natural environment that causes quantum systems to lose coherence. In that case, the smoothness of the macroscopic world would not be an accident, but a consequence of space-time's granular foundation. The continuum would be a mask worn by the discrete. Another possible window into this mystery lies in neutrinos, tiny, nearly massless particles that travel freely through matter and across cosmic distances. Because neutrinos oscillate between different types as they move, even the slightest disturbance in space-time could, in principle, leave an imprint on their oscillation patterns. Experiments such as IceCube, buried deep in the Antarctic ice, watch for these subtle signs. They have recorded neutrinos from the farthest reaches of the cosmos, but so far, their oscillations remain perfectly in line with predictions from continuous space-time. Once again, the universe remains smooth to every test we can imagine. There are times when physicists begin to suspect that nature may be playing a grand joke, a cosmic magician performing its act with such perfection that even the illusion of continuity becomes indistinguishable from truth. The mathematics of both quantum mechanics and relativity work so flawlessly within their domains that it seems impossible that either could be wrong. Yet they cannot both be completely right. Somewhere between the two lies a boundary, and that boundary must hold the key to what space-time truly is. Some theorists have suggested that the evidence might not come from high energy at all, but from complexity. If space-time is an emergent phenomenon arising from the interactions of quantum information, then the transition from the discrete to the continuous may follow the logic of computation rather than that of energy. In that picture, the universe behaves like a quantum computer, its geometry an ever-evolving code that processes information according to the rules of physics. To find discreteness would then mean to find limits on how much information can be stored or transmitted, a kind of informational uncertainty principle. This idea connects the structure of space-time to the limits of knowledge itself. Even in our current technologies, faint echoes of this informational structure may already appear. Quantum computers, though still in their infancy, operate according to principles that mirror those believed to govern the universe's foundation. Qubits, quantum bits of information, can exist in superpositions and become entangled, just like the fundamental fields of nature. Some researchers speculate that space-time might arise from networks of entanglement between such qubits. If so, then our machines may one day simulate, and even reveal, the architecture of reality. The boundary between experiment and existence would blur, and discreteness might no longer be something we look for, but something we build. But for now, the evidence is absence, and absence is its own form of message. Every time a photon arrives precisely when it should, every time a gravitational wave passes undistorted, every time the fabric of space-time behaves perfectly smooth, the universe is reminding us that its secrets are subtle. It does not contradict our theories. It waits for us to refine them. The continuum may not be an illusion at all, but an emergent order so complete that it hides its microscopic structure behind a veil of mathematical perfection. This tension between what we can measure and what we can imagine drives physics forward. It is the quiet engine of discovery. When scientists look into the dark, they do not despair at the lack of light. They learn to see in different ways. And so, the search for spacetime's atoms continues, not only in laboratories and observatories, but in equations, simulations, and dreams. The absence of evidence is not the same as evidence of absence. Perhaps the universe is simply too vast, too smooth, too balanced for us to catch it in the act of discreteness. Or perhaps the evidence has always been there, written in the fabric of information itself, waiting for a mind patient enough to decode it. And so, the quest continues, not to find the smallest thing, but to understand the smallest meaning. To know whether spacetime is made of quanta or continuity is to glimpse how the universe keeps its own memory. For beneath every equation, beneath every law, there lies one ultimate mystery: how nothingness becomes something, how stillness becomes motion, and how the void gives birth to time. There is a growing suspicion among physicists that reality, at its most fundamental level, might not be made of matter or energy or even geometry, but of information. The idea sounds almost philosophical, even mystical, until one realizes how naturally it arises from the mathematics of modern physics. Wherever we look, in black holes, quantum mechanics, or cosmology, we encounter the same pattern. The universe seems to store, process, and transmit information according to rules that look strikingly like those of computation. The suggestion is not that the cosmos is a computer, but that its workings obey principles that parallel the logic of information itself. The seed of this idea was planted by an enigma that refused to disappear: the entropy of black holes. When Jacob Bekenstein studied the thermodynamics of these objects in the 1970s, he discovered something remarkable. The amount of information that could be contained within a black hole, the number of possible microstates describing its configuration, was not proportional to its volume, as one might expect, but to the area of its event horizon. Each tiny patch of that surface, roughly 1 Planck area across, could encode a single bit of information. Stephen Hawking later confirmed that black holes emit radiation, meaning they possess a temperature, and that their entropy indeed equals 1/4 of their horizon area in Planck units. Thus, geometry and information became inseparable. The very surface of space carried memory. This finding shattered the old notion that information could vanish into gravitational oblivion. If a black hole has entropy, it must have microstates. And if it evaporates, that information must be released, not destroyed. The paradox this created forced physicists to rethink what information means in a gravitational context. It was no longer enough to speak of matter or fields. The fabric of spacetime itself appeared to hold bits of data, quantized packets of knowledge that determine the possible configurations of the universe. From this insight emerged the holographic principle, one of the most profound ideas in theoretical physics. Proposed by Gerard 't Hooft and refined by Leonard Susskind, it states that all the information contained within a region of space can be represented by data on its boundary. A 3-dimensional volume can thus be described by a 2-dimensional surface, much like a hologram. In a holographic universe, what we experience as depth and volume might be an emergent projection of information encoded elsewhere. This idea received astonishing mathematical confirmation in the late 1990s through what became known as the ADS-CFT correspondence. In this framework, proposed by Juan Maldacena, a universe with gravity in a higher dimensional anti-de Sitter space is equivalent to a conformal field theory living on its lower dimensional boundary. Everything that happens in the bulk of space, the motion of planets, the bending of light, even the warping of space-time, can be exactly described by quantum interactions on that boundary. The correspondence showed that gravity and geometry emerge from a theory that has no gravity at all, only information and quantum fields. The world we perceive as continuous and geometric might therefore be the shadow of something discrete and informational. If this holographic view is correct, then spacetime itself may not be fundamental. It may be an emergent phenomenon arising from the entanglement of quantum bits or qubits. Entanglement is the mysterious quantum property that links particles across distance, such that measuring one instantly determines the state of the other. When many qubits are entangled, they form a network of correlations that defines how information is shared. Some physicists now believe that the geometry of spacetime is the large-scale manifestation of those correlations. Distances, curvature, even the flow of time might arise from patterns of entanglement. This view is radically different from Einstein's. For him, geometry was the foundation of reality. But in the quantum information picture, geometry is a side effect, a language that emerges from something more primitive, the web of informational relationships between quantum states. The smoothness of space would then be an illusion of scale, the visible result of countless entangled qubits behaving coherently. Just as temperature arises from the statistical motion of atoms, spacetime curvature would arise from the statistical structure of entanglement. Eric Verlinde extended this reasoning even further with his theory of emergent gravity. He proposed that gravity is not a fundamental force at all, but an entropic effect, a tendency of systems to increase their information entropy. When matter moves through space, it changes the distribution of information, and that change manifests as what we perceive as gravitational attraction. Gravity, in this sense, is the universe's way of reorganizing its information content. It is not a pull, but a bookkeeping of knowledge. This perspective redefines everything we know about the cosmos. It implies that the universe is not made of continuous fields, but of discrete informational building blocks, bound together by entanglement and entropy. Every atom, every photon, every event becomes a pattern in a vast informational tapestry. The Planck length and Planck time are not merely small scales, but the fundamental resolution of this cosmic code, the smallest pixels of existence. Below them, the concept of location or duration loses meaning, for information itself cannot be subdivided further. In such a universe, the flow of time might also be an emergent property. Quantum information theory suggests that the passage of time is linked to the growth of entanglement. As systems interact and share information, their collective correlations increase, giving rise to what we perceive as temporal evolution. The arrow of time, pointing from past to future, may therefore be nothing more than the direction in which information spreads. The universe ticks not through mechanical motion, but through the continuous reconfiguration of its informational state. To visualize this, imagine a vast network of nodes connected by threads of correlation. Each node represents a quantum state, each thread an entanglement between two states. The density of connections defines the local geometry. Where entanglement is strong, space is tight and curved. Where it is weak, space expands. The shape of spacetime is thus written into the pattern of connections. A region rich in entanglement appears as a dense, curved pocket of space, a star, a planet, or a black hole. A region sparse in connections becomes the void. The universe becomes a self-weaving web of relationships, with geometry as its visible shadow. This concept resonates with the principle of it from qubit, a phrase coined by John Archibald Wheeler's earlier vision of it from bit. Wheeler speculated that all physical things, the its, arise from binary choices, the yes or no questions that form the foundation of information. The universe, in his view, is participatory, defined by the information that can be extracted from it. Quantum information theory refines this intuition. The bits are no longer classical, but quantum, capable of existing in superposition, entangling, and recombining to form reality itself. If space-time is truly informational, then its discreteness is not mechanical, but logical. It is not composed of tiny grains of matter, but of finite distinctions, differences between possible states of the universe. This means that what we call empty space is anything but empty. It is a dynamic ocean of information, vibrating with potential configurations. Every fluctuation, every quantum event is a bit flip in this cosmic computation. The laws of physics are the algorithms that govern how these bits evolve, preserving consistency and causality across the web. From this viewpoint, even the constants of nature, Planck's constant, the speed of light, the gravitational constant, become conversion factors between different measures of information. They translate between bits, energy, and geometry, ensuring that the universe's code remains coherent across scales. The smoothness of space-time, its apparent continuity, is thus a property of how efficiently this code compresses data. The continuum is compression made perfect. If this vision is true, it unites physics, computation, and philosophy in a single framework. The fundamental question ceases to be, what is the universe made of? And becomes, how is the universe storing and processing information? Space, time, energy, and matter are simply different aspects of that process. The discreteness we seek is not a structure to be seen under a microscope, but a logic to be understood through patterns. The ultimate microscope, in that case, is not a machine, but a mathematical language capable of decoding how information begets reality. Perhaps the universe is a grand quantum network continually updating itself. Every interaction adds a new thread. Every observation reconfigures its structure. From the smallest qubit to the largest galaxy, all things participate in the same computation, unfolding moment by moment according to the laws of information. Whether we perceive it as discrete or continuous depends on where we stand within it, on how coarse or fine our resolution is. The truth may be that both are correct. The discrete gives rise to the continuous, and the continuous gives meaning to the discrete. At this juncture, the boundary between physics and philosophy dissolves. If reality is informational, then existence itself is an act of encoding. The cosmos does not merely exist, it expresses. Every equation, every constant, every particle becomes a symbol in a language the universe uses to describe itself. The task of science is to learn to read that language, to uncover the grammar of creation written not in waves or fields, but in bits of being. And so, the quest to understand whether space-time is discrete or continuous becomes something deeper. It becomes the search to understand how information becomes reality, how the digital becomes the tangible, how quantum possibility becomes classical experience, and how the silent code of the cosmos writes the story of everything. The notion that space-time is not fundamental, but emergent, is one of the most transformative ideas in modern physics. It challenges the very heart of what Einstein believed and what centuries of geometry have taught humanity. In Einstein's vision, the curvature of space-time was the stage upon which matter and energy moved, and that curvature was as real as the planets and stars it guided. But the emerging view suggests something astonishing, that space-time itself may be the product of a deeper quantum reality, an intricate web of entanglement that weaves geometry out of information. To grasp this, one must first understand that quantum mechanics does not describe things as separate. Every particle, every field, every degree of freedom is connected through correlations that defy classical logic. When two particles are entangled, their states become interdependent, so that measuring one instantaneously defines the other, no matter how far apart they are. The universe, seen through this lens, is not a collection of independent entities, but a vast network of relations. It is those relations, the pattern of entanglement, that may give rise to the geometry of space itself. In the late 1990s, this vision took form through the discovery of the ADS-CFT correspondence, proposed by Juan Maldacena. It revealed an exact equivalence between two radically different theories. On one side lies a gravitational universe with curvature, existing in a higher dimensional anti-de Sitter space. On the other side lies a purely quantum system, a conformal field theory, living on its lower dimensional boundary. The two descriptions, though entirely different in structure, encode identical information. The gravitational world of curved spacetime is the emergent shadow of a flat, quantum world of entanglement. Geometry is born from information. This equivalence reshapes our understanding of what it means for spacetime to exist. In the ADS-CFT framework, distances in the bulk of space correspond to degrees of entanglement on the boundary. When two regions of the boundary are highly entangled, the bulk geometry between them appears connected, forming a smooth bridge. When entanglement decreases, the geometry pinches off and the regions drift apart. The famous equation known as the Ryu-Takayanagi formula captures this relationship mathematically. The area of a surface in the bulk is proportional to the entanglement entropy of the corresponding region on the boundary. Space and information are thus two sides of the same coin. To imagine this, think of a spider's web. Each thread represents quantum entanglement, and the tension in those threads defines the distances between points. Where the web is dense, the geometry feels curved and compact. Where it thins, space stretches and opens. The entire shape of the web, its twists, folds, and connections, constitutes the geometry of spacetime. There is no background upon which the web rests. The web itself is reality. In this view, continuity emerges from the vast overlap of countless entangled relationships. The discrete interactions of qubits produce, at large scales, the illusion of a smooth continuum. This concept aligns naturally with tensor networks, a tool developed in quantum information theory to represent entanglement patterns efficiently. A tensor network is a graph where each node corresponds to a quantum state and each link encodes entanglement between states. By arranging these nodes and links in particular configurations, physicists can reproduce the properties of continuous spacetime. The most striking example is the multiscale entanglement renormalization ansatz, or MERA. In this model, the network's layers correspond to different scales of entanglement, and its geometry naturally forms a hyperbolic space, precisely the kind of geometry found in anti-de Sitter space. From the logic of quantum information alone, a curved spacetime appears. This idea has profound implications. It means that gravity itself, the force that binds galaxies and sculpts the cosmos, could be nothing more than a manifestation of quantum entanglement. When the amount of entanglement changes, the curvature of space changes accordingly, producing the phenomena we interpret as gravitational attraction. The motion of planets, the collapse of stars, and the expansion of the universe might all be consequences of the quantum network's information flow. Spacetime is not a container, but a conversation, a dialogue between entangled bits of the universe's code. Such a vision also resolves long-standing puzzles. The information paradox of black holes, which once threatened the consistency of physics, finds a natural explanation here. In the holographic picture, the information that falls into a black hole is not lost, but encoded in the entanglement structure of its boundary. As the black hole radiates and shrinks, the network of entanglement reorganizes, preserving the total information. The horizon is not a surface of ignorance, but a membrane of knowledge, storing the quantum data that define everything inside. The loss of continuity near a singularity becomes the natural consequence of entanglement patterns dissolving at their limit. If entanglement builds geometry, then perhaps the smooth flow of time also arises from the growth of entanglement. As the universe evolves, quantum systems interact and become more correlated. This expansion of entanglement corresponds to the unfolding of spacetime itself. The arrow of time, the direction from past to future, might be nothing more than the direction in which entanglement increases. The Big Bang, in this picture, would not be the beginning of space and time, but the moment when entanglement began to spread across the cosmic network, weaving the first threads of geometry. The emergent spacetime hypothesis also brings together disciplines once thought separate. Quantum information, thermodynamics, and geometry converge into a single language. The entropy that measures information content becomes the same quantity that determines the curvature of space. The equations governing heat and disorder mirror those governing gravitational dynamics. Even the Einstein field equations can be derived from principles of thermodynamic equilibrium when applied to entanglement entropy. Reality becomes an interplay between energy, entropy, and information, a seamless unity of physics and computation. Yet this perspective raises deep philosophical questions. If space and time emerge from entanglement, what then is entanglement itself? What is the substrate from which information arises? Is there an even deeper level beneath the quantum, where the logic of information is born? Some theorists speculate that beyond the qubit lies the principle of quantum causality, the pattern of how information flows and transforms. In that case, the universe might be built not from things, but from processes. Reality would not consist of static entities, but of transformations, a continuous computation whose output is existence itself. This emergent view of spacetime also challenges our intuition about locality. In classical physics, 2 points in space are either near or far based on measurable distance. But if geometry is built from entanglement, proximity is defined by informational connectivity, not by position. 2 particles may be light years apart, yet directly connected through their entangled states. In that sense, space is a map of relationships, not of coordinates. The universe's true topology is not the grid of distances we draw, but the invisible network of shared information. As this vision deepens, it reframes what discreteness and continuity mean. The fundamental elements may indeed be discrete, individual qubits of entanglement, but their collective behavior generates the illusion of a continuous manifold. The smoothness we perceive is the average of innumerable informational interactions. Continuity is not an intrinsic property of space, but a statistical one, emerging from the complexity of entangled quantum data. The same way a movie appears fluid, though made of discrete frames, the universe flows seamlessly, though built from discrete informational states. In this way, discreteness and continuity cease to be opposites. They become complementary descriptions of the same underlying reality. At the quantum level, spacetime is a network of finite informational connections. At the macroscopic level, it becomes a continuous geometry that obeys Einstein's equations. The transition between the two is as natural as the transition from atoms to air, from pixels to image, from note to melody. The universe is both granular and smooth, depending on how closely one listens. The idea that geometry is born from entanglement does more than explain the structure of space-time. It restores wonder to our understanding of existence. It shows that the cosmos is not a static arena, but an active creation, weaving itself from relationships of information. Every particle, every field, every act of observation contributes to that weaving. Reality is not built once and for all, but is continually rewritten. Each quantum interaction, a new line in the story of the universe. And in that story, continuity is not a given. It is an achievement, the harmony of countless discrete notes played in perfect synchronization. Space is not emptiness but music. Time is not motion but rhythm. To ask whether space-time is discrete or continuous may be to miss the deeper beauty, that the two are one, bound by the logic of entanglement, singing the geometry of existence into being. For more than a century, Einstein's smooth space-time has stood as one of the greatest triumphs of human reason. It has predicted with flawless precision the motions of planets, the bending of light, and the expansion of the cosmos itself. It has described black holes and gravitational waves long before we could observe them. Every test of relativity has confirmed its predictions to extraordinary accuracy. Yet even as new theories rise to challenge it, quantum networks, strings, and informational webs, the continuum remains unbroken, undefeated, and indispensable. Those who defend continuity do not do so out of nostalgia, but because the mathematics works. The equations of general relativity, describe a universe that behaves with exquisite precision across all scales we can observe. The structure of galaxies, the dynamics of clusters, the lensing of distant quasars, all match the predictions of a smooth, differentiable geometry. If spacetime were truly granular, these observations should reveal subtle irregularities, minute distortions in motion or light. None have been found. The continuum, at least within the boundaries of measurement, reigns supreme. The same is true for quantum field theory, the framework that describes all known particles and forces except gravity. Quantum electrodynamics, or QED, which governs the behavior of light and charged particles, relies on a continuous space-time background. Its calculations are performed as integrals over fields defined at every point in space and time, with no hint of underlying discreteness. The results are astonishingly accurate. The magnetic moment of the electron, predicted using this continuous framework, matches experimental measurements to better than 1 part in 10 billion. No discrete theory, no matter how elegant, has achieved such precision. This success presents a challenge to the idea that space-time must be fundamentally granular. If discreteness exists, it must reproduce the continuum's perfection, almost exactly at large scales. But if the continuum already explains everything we can measure, why invoke a deeper discreteness at all? This is the argument of the continuum's defenders, that smoothness is not an illusion, but a fact, that infinite divisibility is not a flaw, but a feature, and that mathematics, in its continuous form, is nature's true language. They point to the history of science as evidence. When Zeno of Elea proposed his paradoxes of motion 2.5 millennia ago, he argued that movement was impossible because it required completing an infinite number of steps. The resolution of his paradoxes came with calculus, the mathematics of continuity, which showed that infinite divisibility is consistent, predictable, and measurable. The modern continuum inherits that legacy. It allows infinity without chaos, smoothness without contradiction. Every point in space-time, no matter how small, contributes meaningfully to the equations that govern motion and change. In this light, discreteness begins to look unnecessary, even inelegant. Introducing a smallest length or time complicates the symmetry of the universe. It risks breaking the invariance that makes relativity so powerful. If spacetime were composed of discrete units, what happens to Lorentz invariance, the principle that the laws of physics are the same for all observers, regardless of their motion? A minimal length could introduce a preferred frame of reference, violating one of the most sacred pillars of modern physics. Unless handled with extraordinary subtlety, discreteness threatens to tear down the symmetry that makes the cosmos so coherent. The continuum also has a philosophical advantage. It captures the essence of flow, the unbroken passage of time, the seamless stretching of space, the smooth curvature of the cosmos. It reflects how we experience the world. When we move, we do not jump from one point to another. When we see, our vision does not flicker through discrete frames. The human mind perceives continuity as natural, perhaps because our brains themselves integrate information continuously. The continuity of space-time, then, aligns not only with mathematics, but with perception, intuition, and experience. Of course, defenders of discreteness counter that perception can deceive. Smoothness can emerge from hidden granularity, just as a movie appears fluid though made of individual frames. Yet continuity responds that its strength lies not in appearance, but in functionality. The laws of calculus, differential geometry, and field theory work, because reality behaves as though space and time are infinitely divisible. Even if discreteness exists beneath the surface, it must give rise to an effective continuum so precise that for all practical purposes, continuity is reality. Consider the wave equations that govern electromagnetism, sound, or gravity. These equations assume that fields vary smoothly from point to point. The propagation of light, the vibration of atoms, the oscillation of gravitational waves, all depend on the continuity of these fields. If space were fundamentally discrete, those waves would scatter or distort at scales we should already have detected. The silence of such anomalies speaks in the continuum's favor. It suggests that, at least above the Planck scale, smoothness is absolute. Even in quantum mechanics, where discreteness defines energy levels and particle properties, the underlying mathematics remains continuous. The Schrödinger equation, which describes the evolution of quantum states, is a differential equation over continuous space and time. Its solutions yield probabilities defined across an unbroken continuum of positions and momenta. The quantization that emerges, the discrete energy levels of the hydrogen atom, for instance, is not imposed from outside, but arises naturally from the boundary conditions of a continuous system. In that sense, quantum discreteness is a child of continuity, not its rival. Philosophically, continuity offers something profound, an escape from the tyranny of the smallest scale. If space-time is truly continuous, there is no ultimate boundary to division, no limit to understanding. The universe remains infinitely deep, an inexhaustible continuum of structure and pattern. Every new discovery reveals not an endpoint, but another layer of detail, another refinement of smooth geometry. Discreteness, by contrast, introduces a kind of finitude, a bottom to existence, a final pixel of being. Some find that comforting, others find it confining. In the continuum's defense, there is also simplicity. Nature, as Einstein once remarked, is subtle but not malicious. It tends toward elegance. And few things are as elegant as a universe described by continuous geometry. The equations of general relativity, though complex, possess a simplicity of principle unmatched by any discrete alternative. They describe everything from falling apples to colliding galaxies with the same geometric language. Until a discrete theory can replicate that beauty and precision while predicting something new, the continuum remains the reigning paradigm. And yet, even the defenders of smoothness acknowledge its limits. The singularities predicted by Einstein's equations, points of infinite curvature, are uncomfortable artifacts. They hint that the continuum might not be infinite after all. The continuum fights back not with denial, but with humility. It concedes that its domain may end at the Planck scale, where quantum effects can no longer be ignored. Perhaps continuity is not the foundation, but the emergent consequence of a deeper, discrete order. Or perhaps, like light being both particle and wave, space-time is both continuum and granularity, each description valid in its own domain. In the end, the debate between continuity and discreteness may not be about which is true, but about which is primary. The continuum remains the language of observation, the grammar of our equations, the mirror in which the universe reflects its harmony. Discreteness may be the alphabet underlying that grammar, the invisible code from which continuity emerges. Together they form the dialect of reality, a duality of flow and quanta, of geometry and information. For now, the continuum holds the field. The equations of Einstein and the smooth symmetries of quantum field theory continue to describe everything we can see, touch, and measure. The challenge for discreteness is not to disprove the continuum, but to explain its perfection, to show how a mosaic of quanta can produce a fabric so seamless that even the most sensitive instruments fail to detect its threads. Until that day arrives, continuity stands undefeated, its curves unbroken, its smoothness unshaken, a triumph not only of mathematics, but of nature's own coherence. Between the perfect smoothness of Einstein's continuum and the discrete granularity suggested by quantum gravity lies a narrow bridge built from mathematics and computation. That bridge is called the lattice. It is where the continuous and the discrete meet without contradiction, where equations meant for infinite divisibility are translated into finite steps that a computer can understand. And in that translation, physicists have found not only a powerful tool, but perhaps a glimpse of how the universe itself reconciles the two worlds. Quantum chromodynamics, the theory of the strong nuclear force, is an example of this bridge in action. It describes how quarks and gluons interact to form protons, neutrons, and all other hadrons. The equations of QCD are written over continuous spacetime, but they are impossible to solve exactly. Their complexity grows beyond all limits, like waves entangling infinitely in a storm. To tame them, scientists place the theory on a lattice, a grid of points representing discrete slices of space and time. On this lattice, the fields become variables defined on sites and links, and the infinities of the continuum are replaced by a finite, computable structure. This approach, known as lattice QCD, does not destroy the continuum but approximates it. As the spacing between lattice points shrinks, the results converge toward the predictions of continuous theory. In the limit where the lattice spacing goes to zero, the continuum is restored. Yet even before reaching that limit, the discrete model reproduces real phenomena with astonishing accuracy. The masses of protons and neutrons, the binding energy of nuclei, the pressure of matter under extreme conditions, all emerge naturally from computations performed on this discrete grid. The success of lattice QCD suggests that the continuum may indeed be an effective approximation of something fundamentally discrete. But there is more than numerical convenience in this method. The lattice might mirror the true architecture of spacetime. In a universe built from finite elements, atoms of space and time, continuum physics would arise exactly as it does on the lattice, from the collective behavior of discrete parts. Each point on the grid would correspond not to a physical location, but to an event, a moment of interaction between quantum entities. The geometry connecting these events would not be predetermined, but would emerge from the pattern of causal relationships between them. This idea forms the foundation of causal set theory, one of the boldest attempts to describe spacetime as intrinsically discrete. In this framework, the universe is made not of points in space, but of events ordered by causality. Each event is connected to others by a network of cause and effect, forming a partially ordered set, the causal set. Space and time are not continuous dimensions, but emergent properties of this order. The distance between events corresponds to how many intermediate events link them. The flow of time is simply the growth of the causal network. Causal set theory preserves the essence of relativity while embracing discreteness. Because the order of events, not their embedding in coordinates, defines reality, the theory remains Lorentz invariant. No observer sees a preferred frame. Yet at the smallest scales, the continuum breaks down, replaced by a discrete stochastic fabric. If we zoomed in far enough, the universe would look like a web of linked nodes, each representing a quantum of spacetime, growing one event at a time. The smoothness of space would be a mirage created by the density of connections, just as a grainy image appears continuous when viewed from afar. The beauty of this picture lies in its unity. The same logic that underlies quantum mechanics, the probabilistic progression of discrete events, extends naturally to spacetime itself. Reality becomes a chain of happenings rather than a continuous flow, a cosmic computation unfolding event by event. Each link in the chain is irreversible, preserving causality. The past gives birth to the present, and the present seeds the future, not through continuous evolution, but through quantum transitions. In this sense, the lattice becomes more than a computational trick. It becomes a metaphor for being. The universe may compute its own existence one step at a time, each Planck tick adding a new cell to the cosmic grid. From these increments of space and time, the grand continuum of relativity unfolds, just as a digital screen produces smooth motion from a sequence of frames. The bridge between the discrete and the continuous is not a paradox, it is the process of emergence itself. This insight also carries philosophical weight. It suggests that continuity, so fundamental to human thought, might not be an absolute property of nature, but a feature of perception. Our senses, our instruments, and our mathematics all smooth the discrete into the continuous, just as the mind turns separate moments into the illusion of unbroken time. The continuum may thus be a story told by the discrete, a story so coherent, so perfectly consistent that it feels infinite. And yet, Discreteness alone cannot explain the universe's harmony. The lattice works because it approaches the continuum. The causal set yields meaning only when its density becomes immense. The two are inseparable, like wave and particle, each incomplete without the other. The discrete provides structure, the continuous provides coherence. Together they form the syntax of the cosmos, a dialogue between quantum finitude and geometric infinity. As physicists refine their understanding of these models, new possibilities arise. Lattice approaches now simulate not just quarks, but aspects of quantum gravity itself. Some theories suggest that the very expansion of the universe might reflect the growth of a cosmic lattice, each Planck-scale cell representing a unit of new spacetime. Others imagine that quantum fluctuations continuously add and remove links in the causal network, making spacetime a living, dynamic computation. In all these visions, discreteness is not an enemy of continuity, but its engine, the pulse behind the flow of time. What emerges from this convergence is a vision of reality that is neither purely smooth nor purely granular, but layered. At the smallest scales, the world is a discrete dance of quanta. At larger scales, it becomes the seamless curvature of Einstein's geometry. The lattice and the continuum are not rivals, but successive descriptions, each valid within its domain. The key to understanding the universe may lie not in choosing between them, but in understanding how one becomes the other. The bridge between discreteness and continuity, then, is not merely mathematical, it is existential. It shows that reality can be both countable and infinite, both pixelated and fluid, both logical and poetic. The lattice hums beneath the surface of the continuum like the rhythm beneath a melody, unseen yet essential. Through it, the universe speaks both in equations and in patterns, both in numbers and in flow. Perhaps that is how nature reconciles opposites, not by eliminating one, but by letting each emerge from the other in perfect balance. In that balance lies the beauty of the cosmos, a reality that is digital at heart, analog in expression, and infinitely rich in between. The final question that remains after all the equations have been written, after every experiment has been imagined, is not simply whether space-time is discrete or continuous, but what it means for anything to be real. Beneath the mathematics, beneath the models of geometry and the networks of qubits, there is the human search for meaning, the attempt to understand what kind of universe could give rise to both the infinite and the finite, to both the smooth flow of time and the indivisible grain of existence. Reality, it seems, is a mirror with two faces. One reflects continuity, the other discreteness, and between them lies the mystery of being. If time is discrete, then the universe might tick like a cosmic clock, advancing in steps too small for any instrument to detect. Each Planck moment, about 5 × 10⁻⁻44 seconds, would be one frame in the film of existence, one quantum of now. In that picture, the passage of time would not be a river, but a sequence of beats, like the rhythm of a vast symphony. The cosmos would evolve not through flow, but through computation, updating its state from one moment to the next, the way a quantum computer cycles through its gates. Every instant would be finite, yet together they would create the illusion of continuity, just as countless still images create the motion of a film. If instead time is continuous, then the universe is an unbroken song with no smallest note. The melody of existence flows endlessly, divisible without limit, its every measure blending seamlessly into the next. There would be no ultimate clock, no indivisible tick, only an eternal unfolding of now into later. In such a world, the arrow of time would not emerge from discrete transitions, but from the thermodynamic tendency of systems to move from order to disorder, from simplicity to complexity. Continuity would be infinite patience, the unceasing transformation of geometry, energy, and matter, and perhaps both views are true, depending on the scale from which we look. From far away, space-time is smooth, a canvas stretched across the cosmos. But up close, near the Planck length of roughly 1.6 × 10⁻⁻⁻35 meters, The brushstrokes begin to appear, and the canvas reveals its weave. At that smallest scale, geometry may break into discrete quanta, finite units of area and volume predicted by theories like loop quantum gravity. Yet even there, those units are not static. They pulse, vibrate, and combine, producing the illusion of continuous space when averaged over time. If discreteness and continuity are both true, then they are not opposites but perspectives. Continuity is the large-scale language of the cosmos. Discreteness, its microscopic dialect. The universe may be smooth because it is too intricate for our eyes to resolve, like the seamless shimmer of light that hides the grain of the photon. Beneath the smooth curve of Einstein's equations may lie the digital heartbeat of quantum logic, each pulse giving rise to the next layer of geometry. There is a deeper unity beneath all of this. The laws of nature seem written in such a way that each layer of description emerges naturally from the one beneath it. Quantum mechanics gives rise to atoms, atoms to molecules, molecules to life, and life to consciousness, all flowing upward in complexity. Perhaps space-time itself is part of that same chain, an emergent phenomenon born from the interactions of something even more fundamental, information. If so, the discreteness of the universe might not be spatial or temporal at all, but informational. The bits of reality may not occupy space, they create it. This view transforms the question entirely. Instead of asking whether space-time is made of points or is infinitely divisible, we might ask how the concept of space emerges from the relationships between informational states. In such a picture, distance and time are not pre-existing dimensions, but measures of correlation. Two events are close if they share information, distant if they do not. Geometry becomes a story about connection, and continuity becomes the smooth narrative of entanglement unfolding. If reality is built from information, then discreteness is inevitable. Information, by definition, comes in finite units, distinctions between possible states. There is no half bit, no fraction of difference. Each bit is a fundamental yes or no, a choice between alternatives. But when enough bits interact, their combinations create patterns of staggering richness, patterns that appear continuous. The same principle allows finite pixels to form a seamless image, finite frequencies to form a smooth sound, finite thoughts to form an endless dream. The cosmos itself may be such a dream, an informational ocean whose waves we experience as matter, motion, and time. Yet continuity pushes back with equal force. It reminds us that infinity has always been the language of the universe. The wave function of quantum mechanics spans an infinite continuum of possibilities. The equations of general relativity treat curvature as infinitely differentiable. The constants of nature, Planck's constant, the gravitational constant, the speed of light, connect the finite to the infinite without contradiction. Continuity is not merely an approximation, it is a mode of truth that emerges from the very laws we use to describe discreteness. Perhaps the reason both models persist is that they describe different ways of perceiving the same underlying reality. To the quantum eye, the world is discrete, built from finite quanta. To the classical eye, it is continuous, a fabric of infinite precision. Both eyes are necessary to see clearly. The tension between them is not a flaw but a balance, a duality woven into the nature of existence. At the boundary between discreteness and continuity lies the Planck scale, a horizon not just of measurement but of meaning. Below it, our current concepts of space and time dissolve. There may be no before or after, no here or there, only the raw logic of quantum events. The Planck length is not a wall but a mirror, reflecting our own limits back at us. It marks the point where language fails, where reality refuses to be described by numbers alone. What then is the nature of reality itself? Perhaps it is not a thing at all, but a process, a self-consistent computation that continuously updates its own structure. Each instant gives birth to the next, each quantum event defines the conditions for the following one. The universe does not exist as a completed object, but as an unfolding algorithm, a ceaseless act of becoming. Its discreteness gives it precision. Its continuity gives it grace. Together, they make existence possible. If that is true, then we too are part of that process. Finite beings made of infinite relationships, discrete minds embedded in continuous time. Our thoughts, our memories, our perceptions are quantum events within the continuum of consciousness. The mystery of space-time mirrors the mystery of awareness itself. Both are emergent, both are relational, and both depend on information flowing through a network of interactions. In understanding one, we may begin to glimpse the other. Perhaps in the end, the distinction between discrete and continuous is a question not about the universe, but about perspective. The universe simply is a self-consistent whole that transcends our categories. Whether it ticks or flows, whether it counts or curves, it remains complete, its harmony unbroken. The search for its nature is the search for ourselves, for the pattern that connects our fleeting moments to the eternal structure of all that is. And so, we return to the beginning, the illusion of continuity, the suspicion of discreteness, the Planck frontier, where geometry and quantum meet. The debate may never end, not because it is unsolvable, but because it reflects two truths held in perfect opposition. The universe may be pixelated and smooth, digital and analog, finite and infinite, all at once. Whether space-time is made of pixels or waves, its pattern gives rise to everything we know. If it is discrete, then even eternity is counted. If it is continuous, then there was never a first moment, only the endless unfolding of now.